Hello, today it's my pleasure to talk about Fourier series and Fourier transforms. We're going to discuss first that we're dealing with periodic functions. We're going to talk about magnitude, lead, or lag. We're going to go right into continuous Fourier series. We're going to remember how we did our least squared fit from our general regression. We're going to look at some discrete Fourier transforms, which takes a time series into a frequency series. We're going to look at the FFT function in MATLAB, what it returns, and then we're going to try to take our frequencies and then see what time series would be, inverse version of it. Okay, so, if you just remember your sinusoids or your cosines, sinusoids is sort of a generic term for a periodic function. And if you think about that a periodic function is going to have a particular time interval, a capital T, and that would be in seconds generally. If you think about frequency, how many cycles per second you might have, so that would be lowercase f, that's 1 over t. If we're going to think about angular frequency or circular frequency, you would take that f that you get, multiply by 2 pi. So omega naught would be in radians per second, whereas f would be in terms of cycles per second. So let's say, for example, that our frequency is 1 hertz. So that means that our period would be 1 second, and then our omega naught would be 2 radians per second. So pretty straightforward example. And if we kind of think about, hey, what does it look like if we take that and kind of shift it? So at t equals 1, what does cosine of omega naught t minus pi over 2 equal to? So that curve that we have that we're talking about, the cosine of omega t minus pi over 2, that's actually a sine wave, isn't it? So at 1 second, you're going to be right there, and you're going to be kind of back to 0, if you will. That would be at t equals 1. That would be cosine of 2 pi minus pi over 2, which is cosine of 3 pi over 2, which is 0. If you think about the original cosine of omega t graph shown in a dashed line here, if you think about shifting that to the right, that would be a lag, in this case shown as the minus pi over 2. And the time period could be measured from where the resulting curve starts or crosses the time axis. If you do, on the other hand, if you do a lead, that means that the cosine of omega t is shifted to the left. It's coming earlier, and that would be a plus pi over 2 in this case. And here it's shown measuring the time period from a peak-to-peak kind of perspective. But you could actually have that lead or lag be some kind of generic theta. Plus means it's leading, minus means it's lagging. When you look at it from a cosine graph perspective. So let's take a look at this a little bit more. Let's think about a particular magnitude that is multiplying a cosine of k times omega naught t plus a theta k. So k is called a harmonic, and the theta k is an associated lead or lag that goes with that harmonic. The c sub k would be the magnitude that also goes with that harmonic. So if we think about just generically breaking out our normal cosine of the sum of two angles, we would have cosine, we would have c sub k times cosine of k omega naught t times cosine of theta k, and then minus c sub k times the sine of k omega naught t times the sine of theta k. So note that this minus it results from the cosine of the sum of two angles. So I always remember is if it's the sine of the sum, the SIGN, the sign is the same. But when it's cosine of a sum, the sign actually swaps. So remember that sort of breakout here. And the way that you see these Fourier sort of representations is they will take the c sub k times the theta k, cosine of theta k, and they'll call that a sub k. So they'll call that a real part. And then they'll take the minus c sub k times the sine of theta k, and they'll call that b sub k. And we end up calling that the imaginary part. So typically, you'll see the format. It'll be a sub k times cosine of k omega naught t plus b sub k times sine of k sub k times omega naught t. The next thing I want to talk about is continuous Fourier series. Say you have a periodic function. In this case, I'm just looking at a very crude square wave, a very crude square wave, which from a function perspective, you could write that function of time as some magnitude for the first half of the cycle, and then minus some magnitude for the second half of the cycle. So here you see that I've got a time a period of 4 seconds. I've got a magnitude of 2. So there's my example. So a Fourier series of a periodic function can be written like this. So, and I've written it as f sub f. It's going to be some kind of offset, plus you're going to take a sequence starting with k1 all the way up to infinity of a sub k, little a sub k, times cosine of k omega naught t plus b sub k times sine of k times omega naught t. So, and then the way the Fourier series works is that the a naught will be an integral of the function over time from 0 to the period t, and you divide by 1 over t. So it's sort of the average value. And then the a sub k is 2 over t times the integral of 0 of the function times cosine of k omega naught t integrated over time from 0 to t. The corresponding b sub k is going to be the same thing, but it's the function times the sine of k omega naught t that's integrated. So what's amazing to me is sort of like similar to Taylor's series is I didn't know if I believed it, but this is going to be true. It's going to be perfect that f sub f is going to equal that f sub t, even though this f sub t has some discontinuities. It would equal that perfectly. But to do that, that summation that you have here is from 1 to infinity. So you have to take it very, very far in order to see that perfect equality there. Remember that the fundamental frequencies are omega naught equals 2 pi divided by the period. And then the ordinary frequency is 1 over the period. And don't forget that the K here is identifying particular harmonics, as we call them. Okay, so let's take this example of the square wave and go through and see what that Fourier series looks like. So this is very interesting. All right, so I'm going to go ahead and break out, I just rewrote this, but I'm going to go ahead and break out these integrals, and we'll have to do it piecewise because of the discontinuities. So what we'll do is we'll bring in the function as m, and then we'll split up we'll break it into discrete pieces of time. So we'll go 0 to t over 2, integrating m, and then we'll go t over 2 to t, integrating the minus m. And then when you put this all together, you're going to have t over 2 there. You're going to end up subtracting off the t over 2. So the a naught is 0. So the a naught is really an offset. And, you know, the square wave is balanced over the y-axis, right? So they call it a DC component, or the offset. You know, that's going to be 0. Okay, and then the next thing I did is try to figure out what the a k's are. So the a sub k's, we're going to be integrating f sub t times cosine. So let's see what that looks like. We're going to break it up into the two segments. We're going to have the m for the first half, and then we're going to have minus m for the second half. And when we integrate cosine, we're actually going to get sine, and we're going to have a 0 to t over 2 and t over 2 to t. So what I did is I created like a table just to make sure that I didn't get this kind of goofed up, and then I did it for, discrete values of k, starting at 1, and I went all the way to 4 in this example, and I could see that it didn't matter. Sometimes you get patterns, and here, it doesn't matter. We're going to get 0 for the sine pieces for every zero, every t equals 0, every half t over 2 step, and you end up getting 0 at the end. So the a sub k's are all going to be 0 from 1 to infinity, so you don't see anything there. Okay, but now trying to take a look at the b over k's, things get a little more interesting here. So what I did is the same kind of thing, and then we're doing the sine k here. Sine k integrates to minus cosine. So I've got the cosine, I just pulled the minus out here. 0 to t over 2, t over 2 to t. So I created my little table again, and it turns out that only the odd k's are going to matter because the even k's are just kind of kill each other. So the even k's are going to all be, b sub k's are going to be 0. But for the odd k's, you're going to have this factor in front. And then, kind of breaking out what this is going to be, you're going to have a minus 2, minus 2. So that's going to be a minus 4. Minus 4 times minus 2 is 8. And then you end up kind of simplifying it because you can, of course, because omega naught is 2 pi over t. So you're going to end up kind of killing the t's here. And you end up with just the 2 pi. And then there's the simplification of 4m over k pi. So that's what our b sub k is going to be. So very, very nice result here that we can put to good use. So what I did is I created a real, quote-unquote, real square wave function in MATLAB. And I used the modulo function in case the time, the little t coming in is more than a big T, the period. So just making sure I understand what part of the period or what part of the cycle I'm in. So it's going to be plus m or minus m depending on that. And then for the Fourier square wave, I'm going to have the time coming in, the period coming in, the magnitude coming in, but I'm also going to want to know how many terms am I going to use here. That's going to help me kind of stop the for loop that we have down here. So I kind of adapted this, to be honest, from different sort of cycles. This particular cycle, there are no sign changes on the b. The b is always going to be 4m over k pi, and that's going to be only for odd ones. So in my for loop, I'm going to go k starts at 1. And then I'm going to go odd. I'm going to skip, I'm going to skip the 2. I'm going to go 1, 3, up to 2m minus 1. So in the examples, let's say that m coming in is 4. So that means I'm going to go 1, 3, 5, and then 7. So four terms would give me 1, 3, 5, 7 for k. And let's see how this kind of works out. So there's no a naught. So I set y equal to 0 and initialize y equal to 0. And there's no a sub k. So the only thing I've really got working is the b sub k. And that's only when k is odd. And I'm going to only go 1, 3, 5, 7. So that's kind of the sort of the pacing of this. And the SIGN, as I said, in the square wave is not actually changing sign. So I bring it in as plus 1, and I commented out the thing where I alternate the sign. So this 4m divided by k minus pi is the b sub k. And then the sine, this part here, the sine of k omega naught t, the sine of k omega naught t is right there. So this is how I create this Fourier square wave, and then I return the y value, and that's going to be the value of this quote-unquote function that's taken to the m terms. Okay, so here's how I implemented it and tried to plot it. So I created a concatenated sort of series. I did a real square wave where I initialized the real square wave, and then I did the Fourier representation with one harmonic, with the third, with the fifth, with the seventh. So I have 4 different ones, and that's going to correspond to 1, 2, 3, 4 additional terms. And I also did the time period of 4 with the magnitude of 2. And then plotting, just plotted them all, and then actually added a legend for it so you could see it. So very nice. You can see it's balanced. So the first one is a square wave. You see that very nicely. And then the first harmonic is just a sine wave. That sort of matches it. And then the third harmonic is that one. And then the fifth, with the fifth harmonic, we see that one. And then the final one that I'm showing here is the seventh. So each one progressively becomes closer and closer to that square wave. I actually continued this quite a while, actually, but I'm showing you up to 15 here. So this is as we progress. So that'd be 9, 11, 13, and then 15. So the higher we go, the more it becomes closer to that actual square wave. So very, very interesting how this works. Hello, hopefully you remember your linear regression and general regression from earlier. Here we're going to try to set up a situation where we're going to try to fit some data. We're going to try to fit a function a0 plus a1 cosine of omega naught t plus b1 times sine of omega naught t. We're going to try to fit that onto the data, onto some periodic data it needs to be, so that we find our a0, our a1, and our b1. There's going to be a residual e, and we're going to try to do this where we minimize the sum of squares of the residuals. So that's what this is, if you remember that. And this, when I did this, in the general sense, I took the equation here, this 15.7, and remember what I did is I wrote it in terms of a matrix equation, and here's what it would look like if I were to do that. One thing that I need to point out to you is that we're going to look in our example, we're going to have 10 points. The delta, the capital T is going to be 1.5 seconds, so that means that the delta T is 0.15 seconds. So the y data goes from 0 up to 9 delta T's. In this case, I've got n is 10, so I'm going to take it up to n minus 1 delta T, or 1.35 seconds. So you're going to see that. So there's a little bit of confusion in the book of what the time period is, but the time period is really n times delta T, and that the data goes from time equals 0, and the time goes from time index 0 all the way to time index 9. So that would be t 0 equals 0, and then 1 delta t, 2 delta t, 3 delta t, 4 delta t, 5, 6, 7, 8, 9 delta t's in this example of 10. I've got 10 times that I'm bringing in. I've got 10 y datas, and then I've got 10 different cosine of omega naught t's, and then 10 different sine of omega naught t's. So I set up this matrix of 10 by 3, and I set up a right-hand side of 10 by 1. I've got 3 unknowns, and how I did this when I described general regression with you is that I talked about an equation zx equals b. It's an over-constrained linear system. So what you can do is you can do a least squared fit of it. This is what I taught you. You multiply both sides of the equation by z transpose, and then you can invert it. Z transpose z inverted, and then that's your x solution to the equation. And this z transpose z So that's what was over here. So I was a little concerned when I saw this, and I tried to go back and make sure that it agreed with the general regression, and it does very nicely. So the x is going to be my a naught, a1, and b1, and then the right hand side is as shown. That's going to be z transpose the b, and very nice there how that works out. So this part here, I was a little concerned about that, so I kind of did some studying on this, and because they're claiming that these off diagonal pieces are all going to be 0, and it's actually true. So I looked at this and I was a little bit intimidated by it, but then I remembered, hey, if I were to just look at, these are periodic functions, if I were to just look at these things integrated from 0 to 2 pi over the full integral, then yes, the sine does integrate to 0, and that's the same as taking it from 0 to t and divided by 2 pi. Same thing here, taking the sum of those sine of omega naught t's and dividing by n, so it's the same thing. Cosine also, and then the cross one, the sine and times the cosine, that also vanishes. Sine squared cosine squared does yea verily equal half when you do the integral and then you divide by 2/2. So this is true. Very interesting how I found that out. So then I took the example in the book and just kind of double checked it to make sure it kind of made sense. Yeah, the time integral, we're going in delta t's of 0.15 seconds, and we're doing 0 all the way to 1.35. So the idea is that if you were to go back to the 1.5, the 1.5 at the 1.5 timestamp, that would actually be equal to the y that you began with. So it's supposed to be periodic, and that's how it works. So just to kind of put a bow on this, so they're claiming that the omega naught is 4.189. So I took the what I thought was from n equals 10, the time being 1.5 seconds. I did my fundamental frequency is 1 divided by that time, or 1 divided by 1.5 hertz, which is 2/3 hertz. So I brought that in and multiplied it out by 2 pi. And yes, I do get the 4.189 radians per second. Then I just kind of followed the results here that we got from our least squared. So remember, this is the function we're trying to fit on the data. So it says, that the a naught is going to be your sum of y divided by 10. So I've got 17 divided by 10. So that's looking good, 1.7. And then I have a1 is going to be the sum of y cosine of omega naught t times 2 divided by n. So I got 2 divided by 10, and then I take the result of this column, and I get 1/2. And then the last one is the b1, so I take the sum of this column, the y times the sine of omega naught t's. I get 4.33, and then I'm multiplying by 2 divided by n, so that's 2 over 10 again, and I get minus 0.866. So this is right. This is right. I agree with this. So that fits that equation very nicely. This, however, is not correct, because if you take the arctangent of a minus number divided by a positive number, you don't get a positive angle. So this is wrong, and it should be that you're going to take the inverse tangent of minus b over a, and that's going to be minus a minus, and you end up with that plus. So this is how it should look. But this is right in that you're going to end up with a positive angle there, and you can kind of see it how they've drawn it. So this is, I think, is going to be like a pi over 3 kind of advance to the cosine function. You see that it's before, and you see the C1 kind of here. That's going to be 1 in this case. So remember that the reason why this is a little bit messed up is that there's this minus sign when you're looking at the cosine of the sum of angles. There's a minus sign that goes there. So that plus does go correctly with that minus. It's just that they interpreted the theta incorrectly. It should be minus that minus value that it had, so that you get the plus angle that you want. Okay, so if you think about how to take the least squared and extend it to additional harmonics, it would work. It would work. So I thought this was a very important thing to say here, and it kind of leads us into where we're going to go with the fast Fourier transform, or FFT. So we're going to talk about a time interval that sets the capital T. And then we're going to have n data points so that the time period is n times delta t. So delta t is the time divided by n, and that's an easy one to get. So let's say you have some raw data that goes from 0 to n minus 1 times delta t, right? So remember, the data is periodic. So if you were to kind of think about what the y value at n times delta t, well, that's going to equal the very first y that you began with at t equals 0. The sampling frequency is 1 over the delta t, and there's an important theorem here, Nyquist sampling theorem, is that you can only estimate up to the fs divided by 2. So you can go halfway to fs for your estimation. So we're going to take and look at a discrete Fourier transform where we take a time series and we go to frequency. And that's what the FFT does. And then, of course, we can do the converse to kind of check ourselves. So I'm going to use a contrived example from the book. And what I mean by that is I'm going to start with a very known periodic function. And then I'm going to do the FFT on it and kind of verify it, because I want to see, hey, and here's my function, 5 plus cosine of 2 pi times 12.5 t. Plus sine of 2 pi times 18.75 t. That's going to be my function, and I know it's periodic. I can see what the fundamental frequency is because 2 times 6.25 is 12.5, and 3 times 6.25 is 18.75. So I know my fundamental frequency is 6.25 hertz. So this is going to give my time a period of 1 divided by 6.25, or 0.16 seconds per cycle. So I got some raw data from this contrived example, and then I go throw it at the FFT, and I'm expecting to get a 5 offset, and then I'm expecting to only get a harmonic at 2 because of this, and a harmonic at 3 because of this, and kind of how, remember the A-B kind of thing. So really, I should be getting an A for the second harmonic and a B for the third. So let's see what we get on this. So I've set up some simple code here. I got my time period set at 0.16. Very coarse, eight data points. My delta t is going to be t over n. My fundamental frequency, 1 over t. So here's where I set up my time, or my x, I called it here. So my time is going to go from 0 in delta t increments up to and including n minus 1, which would be 7 delta t. So one thing you may not be comfortable with is what's called an anonymous function. It's very simple because you can define a function in one line. You just say at t. So t is going to be the argument, and I'm going to be bringing it in. So I've got the 5 from our contrived example. I've got the cosine of 2 pi, the 2 harmonic, and then I have the sine of the 2 pi times the 3 harmonic. Right? So then I've got my function kind of set up. So I set up my raw y values. And then I wanted to see, hey, I want to see what this thing looks like. Very fine. So I just called it fine here. And I wanted to see 500 data points. I went ahead, just for giggles here, I went ahead and did 2 time periods. I wanted to see it kind of continue. So then I wanted to plot the raw data as circles in black. And then I'm going to plot the very fine over the 2 periods in red. And then I added some verticals to show the demarcation of the cycles. So let's see what it looks like. So here's what it looks like. I've got the red is showing the smooth over 2 cycles. And then I see the raw data in circles. I've got starting at 6. Remember, you've got the 5 is the offset, but the cosine is going to add a 1 to it. So I've started at 6, and then I go through. I've got 1 data point. That's the first one. 2, 3, 4, 5, 6, 7, 8. So 8 data points. That's at 0.14. That's going to be at 7 delta t. And I don't show 8 delta t, but I've got 8 data points showing 1, 2, 4, 5, 6, 7, 8. Yes. All right. And then this ends the first cycle, begins the second cycle. So you can kind of see how it goes. And then I didn't put a semicolon after that. So you can see what my X values look like. Yes, I do stop at 0.14, and I do have 8 of them. That's going to be my time. And then I just, hey, what is, if I were to type just func1 here at the command prompt, it kind of shows what I gave it initially. So I've got my raw data kind of set up. Now I want to look at what the FFT thing is going to give me. So let's see what happens. So here's from the book's example that I've been emulating here. Okay, so there's that crazy example. So it's set up that the sampling frequency is going to be 50 hertz. It's going to be, the delta t is 0.02. It's got 8 samples over that sampling frequency. So the whole time is going to be 0.16 seconds. And yes, this is correct. I agree with this. The Nyquist is going to be half of the sampling frequency. So that's going to be 25 hertz. So we can sample, we can predict our FFT should be good up to 25 hertz. And then you see here that the fundamental frequency is 6.25. So the way the book kind of sets it up, and I'm going to show you how I do it a little bit more here, is they kind of set up the data. So the raw data is y. It's going to equal basically that function, and then they call it capital Y, is going to be the coefficient. So they call the FFT of y, and then they divide by n number of points. So they do that, and they get they get the real part from the FFT call. They get the real part as being 0 for the fundamental harmonic. The imaginary part is 0 for the fundamental harmonic, and that's correct. There's no fundamental harmonic in here. And then for the 2 harmonic, which is going to be 12 and a half, they get a half for the real part. And looking over here, the real part goes with cosine, so should really be 1. But they're showing a half, and they get 0 for the imaginary. That's correct. And then for the 3rd harmonic, they get 0. 18.75, they get 0 for the real part, and they get minus a half for the imaginary part. So that's not right. It should be plus 1, and they're getting minus a half. So I'm going to show you how you have to kind of finagle these things that you get back, and why they kind of are off by, here they're off by factor 2, here they're off by factor of minus 2. So we'll talk about that in a second. And then the 4th harmonic, they've got 0, which is correct, right? So you only have a 2nd harmonic for cosine, the real part, and then you have a 3rd harmonic for sine, which is going to be the imaginary part, and then 0 for both for real and imaginary in the 4th harmonic. And then remember that this is correct. The data showing goes from 0 to 0.14. It doesn't go all the way back to 0.16. Okay, so let's take a look at how I did it. This is a good start, but it's actually not good enough because of these issues here. Let's go take a look at it. So you can see my code here on the left. I set the time period, I set the number of points, fundamental frequency, delta t. I set up my anonymous function again. I set up my x's. I go ahead and get my raw y's. I do the FFT of y divided by n. Here I called it yk. So this is what they did, right? And it turns out that what is returned, this is correct. What is returned by the FFT and you can see my yk here. So this is what's returned, okay, by the FFT function, but you can only use part of it. You can only use about a half of it, because what happens is the very first one that you get back is going to be a 0, and it's going to be a real, and it's 5, and that's correct, as you know. And then what happens is you're going to get, starting at index 2, you're going to get the first harmonic, second harmonic, third harmonic, fourth harmonic, and you're going to get a complex number, real part, imaginary part, right? And it's going to correspond to the fundamental frequency, 6.25, 2 times that, 3 times that, 4 times that. So that's kind of the pacing of it. And then you really have to stop after that last one. You have to stop, and what happens is it kind of reflects it. If you give it real data, it'll give you in the reverse order. The 8th one will be they call it minus k, or minus 1, minus 2, minus 3. So there's sort of a flipping of it. I don't associate frequencies with these. To be honest, I just discard them. And you see how I do that is I take the ceiling of n plus 1 divided by 2. So I kind of just truncate, and it's going to end up being, if n is 8 in this case, it's going to really return 1, 2, 3, 4, 5. It's going to return 5 because of that function of that 1 to the ceiling of 8 plus 1, 9. So that's going to be ceiling of 9 halves, which is going to be 5. It's going to return the first 5, and that's what I want here, kind of discarding these. And then I go ahead and take that first one and assign it to A naught. And then I take the real part of 2 to the end of that. So that's going to give me the 2, 3, 4, 5. And I multiply by 2. Remember I was saying that the A's are off by 2. And then the B's, again, the B's seem to be always off by a negative sign. So you always got to chase negative signs on the B's, as we already talked about earlier. But I really need to double them. So those are going to be my sign coefficients. Okay, and then there's kind of a quirky thing that happens on odd ends versus even ends. In this case, it's an even n. So the fourth harmonic, so if it's in case of an 8, for example, you take 8 and divide by 2, that particular harmonic will always be real. Here it's all 0, 0, but that if n is even, that mid harmonic, the fourth harmonic here, will be real, and it won't have a conjugate. So these the 1, 2, 3, those are conjugates of the original 1, 2, 3. So 6, 7, 8 are flipped in order, and these values are actually conjugates of what you had in the first part of it. Okay, but if it's even, you don't have a conjugate for that mid frequency, or the middle point there, the 4. But if it's odd, if n happened to be 9, it would have a minus 4 in the thing, but you still would take only 0 through 4, or the index 1 through index 5. So that would work out. I think the best way to do that is kind of look at some examples to see what I mean. But this is how I fixed it here. And this would happen. I check to see if n is even. That's how I check it. And then I take that A and go back and put it back as the original A, divide by 2 for what I had. Okay. In this case, it didn't matter anyway because it was 0, 0. But here's what I end up with at the end of the day. I get my A naught as 5. I get my A for the second harmonic. That's going to be the cosine is a plus 1. And then for my B, the 1, 2, 3, the third harmonic is a plus 1, which is correct for sine. Okay, let's see how this looked in a plot type of thing. So I did 2 figures. The first figure, I plotted the raw data, X and Y, and then I also plotted a blue line here that is going to be a YY. So the YY is coming from taking the coefficients that I got from the FFT manipulated coefficients I got from the FFT and sort of projecting how that would look if I were to start with YY being A naught, and then I go in and add the harmonics parts, the harmonic terms, and see what that looks like. And then I did a smooth function where I did very, very fine from 0 all the way to t. And so I plotted those three, and that's what's shown in figure 1 here. So you can see the raw data in the circles. I've got 1, 2, 3, 4, 5, 6, 7, 8. Yes, and I don't repeat the point where it would transition back to starting the next cycle. So that looks correct. The reconstructed time series we got from the inverse is shown as blue, and it goes through the same points. So very, very nice there. And then the smooth, you see that in green. So that is representing the function 5 plus cosine of 2 pi 12.5 t plus sine of 2 pi 18.75 t. So when t is 0, we're going to be starting at 6 because that's going to be a 1, that term. We start there, and then, we go through the normal sine, the normal periodic function here. And our period is 0.16 seconds, as we see here. 3 divided by 0.16 is 18.75, and 2 divided by 0.16 is 12.5. So that's figure 1. And then figure 2. Oh, remember that this is a contrived example. The fit for the real data would not be perfect after you did the inverse type of thing here. Okay, so let's look at what this looks like in a frequency spectrum. So what you do there is you're going to plot the k's along this axis, and when k is 0, then you're going to get the 5 that you have up there for A naught. And so you see the Fourier series are going to be green circles for A, and it's going to be red squares for B. So there's no B0, so you only have an A0, and then the A1 and the A1 and the B1 are both 0. And then for 2, we have a cosine, so we have a real 1 for our A2. Our B2 is 0, so we have that. And then for 3, our B3 is 1, and our A3 is 0. So these are correct. So we see the 5 is shown up here. We see that this 1 here is corresponding to this term, the 2 harmonic. And then we see this 1 here is corresponding to this term, the magnitude of the sine, for the 3rd harmonic. And then the 4th harmonic is 0, 0, as we said, for both the A and the B, real and imaginary. Remember, this is a contrived example, so the fit for real data would not be perfect. But it was really good, instructive here to see, okay, we started with something so that when we do the FFT, we have an expectation of seeing an equivalence of what we started with. So now we can kind of use the FFT, I think, with some confidence. So we discussed periodic functions, continuous Fourier series. We looked at a little bit at least squared fit. We looked at an example there. Then we went right into discrete Fourier transforms, time to frequency. That's what the FFT does. And then we did the inverse. Hey, how do we take that frequency stuff and then go back to time? So anyway, so that is a really good wrap on Fourier series and Fourier transforms. I hope you enjoyed it.